4.3 Binomial distributions. So this is a different kind of distribution than what we saw in the last one, where we had the uniform distribution. In a binomial distribution, we have only two possible outcomes, either success or failure. Okay, and each of these outcomes would have its own probability, but the total of which will add up to 1 or 100%. Okay. So the binomial distribution has a specified number of independent trials, and then in which there are only two outcomes, success or failure. And the probability of a success is the same in each and every trial. So the probability in the binomial distribution, the probability of x successes in n independent trials is given by this formula. The probability of your successes is equal to, we're using a combination here, so it's n choose x times the probability of your successes times the probability of your failures, which is P and Q. So let's look at applying this binomial distribution to a problem. So an electronics manufacturer produces precision resistors designed to have a tolerance of plus or minus 1%. From quality control testing, the manufacturer knows that about 1 in 6 is actually within just 0.3% of its nominal value. A customer needs 3 of these more precise resistors. What is the probability of finding exactly 3 such resistors among the first 5 tested? So some of these bolded words here kind of clue in on what the values that we need for the binomial distribution formula. So the fact that it says here 1 in 6 is actually within nominal value. So this 1 in 6 is a kind of probability of success, right? The probability that we'll get this really precise resistor within 0.3% tolerance, right? So tolerance meaning it's just like how far it deviates from its intended design specification, right? So if it's designed to work within a certain number, well, it's going to be plus or minus 1%. But the really precise ones are going to be plus or minus 0.3%. So you have a 1 in 6 chance of that happening. So the probability of the really precise resistor is 1 out of 6. So if that's your probability of success, then the probability of failure, the probability of not getting a precise resistor would be 5 out of 6. Okay, because the sum of the successes and the failures have to add up to 100%. Okay, so how many trials are we going to do? N is the number of trials. So N is a popular letter we've been using all course to represent that. So number of trials. So the number of trials here is going to be 5. First 5. We're going to test the first 5 resistors. And we're interested in the outcome. So X is the number of outcomes, right? So X says here X successes. How many successful outcomes are we going to have? Well, we want exactly 3. Exactly 3. So 3 of those resistors have to be precise. Okay, so now we have the elements that we need for our formula. So if I'm going to find that probability, so the probability, this is the formula given to us. So n choose x times the probability raised to the power of x times the probability of failure to the power of n minus x. So we're interested in finding the probability of exactly 3 outcomes, which is equal to 5 choose 3, because we're trying to find 3 successful tests out of 5 tests. Order does not matter, which is why we're using combinations here. And the probability of success is 1 out of 6 raised to the exponent 3 times probability of failure, 5 over 6 raised to the exponent 5 minus 3, right? So think of this as like probability of independent events. So probability of getting 3 successful tests times the probability of getting 2 failures, right? So we're multiplying them like this. So if we multiply all of these values out, we get 0.0322, or we can say approximately 3.2%. So therefore, there is a chance. Well, I should say something like this. The chance of getting 3 of these resistors is 3.2%. It's really difficult to get those three resistors. Small probability. Okay, let's talk about expectation. So expectation for a binomial distribution. So the expectation for n independent trials is e to the x equals n times p. So since the probability for all trials is the same, the expectation for success in any one trial is p. Okay, so let's look at an example. A card is repeatedly drawn from a deck and then replaced. What is the probability that in 20 trials an ace is drawn 3 times? Okay, so let's look at the probability of drawing an ace, right? So what's the probability of drawing an ace? Well, there are 4 ace cards in the deck of cards out of 52 possible outcomes, 52 possible cards. If I were to write that fraction in lowest terms, it would be 1 out of 13. So the probability of a success, P, is going to equal 1 out of 13, which means the probability of failure is going to be 12 out of 13. Okay, because you want P and Q to add up to 100%. Now we're doing 20 trials, so n is 20, and we're interested in finding the 3 successful outcomes. So 3 successful drawings of an ace. Okay, so expressing this as a binomial distribution problem, the probability formula is going to be n choose x times p to the power of x times q to the power of n minus x. Okay, so we're multiplying the number of ways we can get 3 successful outcomes out of 20 trials. So 20 choose 3 times the probability of a successful outcome happening 3 times. So 1 over 13 to the power of 3 multiplied by the probability that will fail two times. Sorry, 17 times, because out of 20 trials, 17 will have to be failures. So 12 out of 13, the exponent 17. Okay, and that's going to give us an answer of 0.1331, or approximately 13.3%. So therefore, the probability of drawing an ace is about 3 out of, sorry, drawing an ace 3 out of 20 times is 13.3%. So what is the expected number of aces drawn in 20 attempts? So you conduct this 20 trials, what is the expected number? So you would expect, so meaning expectation, meaning like what on average would you expect to draw, how many times to draw an ace? So you take the 20 trials, multiply the probability of drawing an ace, and that would result in 1.54. Okay, so on average you can expect to get 1.54 aces in 20 attempts. Just simply taking the number of trials times the probability that you're drawing an ace. Okay, example number 3. TJ is getting a new cell phone number. First 3 digits of the number will be 446, and all combinations for the 4 remaining digits are equally likely. Okay, TJ's favorite numbers are the prime numbers 2, 3, 5, and 7. Part A. Calculate and graph the probability distribution for the number of these prime digits in TJ's new number. So, now, how many numbers are there to choose from? Well, we have the digits from 0 to 9, which is 10. So we have 10 possible outcomes. And TJ's favorite outcomes, so we'd consider these successes if we were to get 2, 3, 5, and 7, or 7. So you have 4 out of 10 ways to get a successful outcome. So our probability here is going to be 4 out of 10, which means the probability of failure will be 6 out of 10. And we need 4 more numbers to complete the phone number. So there are 4 trials here. Okay, and now instead of having exactly 4 exactly all 4 trials being successful, we're looking at the distribution of the possible probabilities. We can have 0 all the way to 4. We can have the successful outcomes. You can have 0 successful outcomes. You can have 1 successful outcomes, 2 successful outcomes, or 3 or 4 successful outcomes. And we're interested in finding that distribution. Remember, this is about probability distribution, looking at the probabilities of all the possible outcomes. Okay, so let's look at having 0 prime numbers as an outcome of getting 4 more numbers. Okay, so let's look at that probability, and we're using the binomial probability to do that. So again, as a reminder, that formula is P of x equals n choose x times the probability of success times the probability of failure. Okay, so if we have 4 numbers, 4 trials to do, so we're picking 4 more numbers. So 4 choose 0, 0 meaning we didn't have any prime numbers show up. So then we multiply by 0.4, the probability of success. So 4 out of 10 is just 0.4 raised to the exponent 0 times the probability of failure, 0.6 raised to the exponent 4. And that's going to equal 0.13. Okay, what if TJ ended up getting one of those last 4 remaining digits as a prime number? So here we would have 4 choose 1 times 0.4 raised to the exponent 1 times the probability of failure, 0.6 raised to the exponent 3. And that's going to be 0.35. All right, so what if instead he had 2 prime numbers show up? Let's multiply the probability of success, so 0.4 to the power of 2, because you have 2 prime numbers. Multiply by the probability of failure, 0.6 to the power of 2. And altogether, that's going to be 0.35. And then if we had 3 prime numbers, 0.4 to the power of 3 times 0.6 to the power of 1, and that's equal to 0.15. And then finally, what if TJ got all 4 digits exactly the way he wanted them, 4 prime numbers? So it's 0.4 to the power of 4 times 0.6 to the power of 0, which is equal to 0.03. Very small probability that would happen. But now that I know all the probabilities for all these different outcomes, I can now model this probability distribution. So for the first one, we're at 0.13, and so I'm looking at drawing a bar like this, and that's the first bar. And for 1 prime number, we're at 0.35, so I'm looking to draw a bar up here. And for 2 prime numbers, we're also at 0.35, so another bar up here. For 3 prime numbers, we're at 0.15, so a bar over here. And for 4 prime numbers, we're at 0.03, so a really small bar down here. Okay. Now, so these are all the outcomes, and now of course there is rounding, but when you add them up, it's really close to 100%. All right, so what is the expected number of these prime digits in a new telephone number? So on average, what would you expect to get? So if expectation is equal to n times p, and you look at, well, I'm interested in getting 4, so I have 4 trials here, and the probability of getting a prime number is 4 out of 10. So which is equal to, when I multiply these two values, I get 16 over 10 or 1.6. Okay, so what does this mean? It means TJ can expect to get 1.6 prime numbers that he likes in his new cell phone number. Okay, because remember, this is all about the number of prime numbers. X is the number of prime numbers. So 1.6 has to represent the number of prime numbers, not the actual number, but the number of prime numbers. So therefore, TJ can expect to get 1.6 prime numbers that he likes in his new cell phone number. That he likes in his new cell phone number. Okay. Example 4. Smarties make candy-coated chocolates, 30% which are red, The production line mixes all the colors and randomly packages 10 per mini box, Halloween size. What is the expected number of red Smarties in a box? So expectation, when you see expected number, use the expectation formula. Okay, so if we're doing 10, so there's 10, 10 per mini box, so 10 trials. Think of it as the number of trials when you're putting in a Smartie candy inside a box. And the probability of getting a red is 30%, so we'll say 0.3. So 10 times 0.3 is equal to 3. So therefore, on average, you can expect to get 3 red Smarties per box. So you can expect to get 3 red Smarties per box. Okay. What is the probability that at least 3 Smarties in a box are red? So when you're dealing with this thing that looks like at least, well, it looks like, think back to the probabilities chapters we did back in the beginning, of course, you may need to use something like an indirect method, which is the hint that I give you right here. So before we can do any of these formulas, I need some values. So the probability of success is 0.3, so that's my P. The Q value is the probability of failure. So out of 100%, if 30% is the probability of success, then 70% must be the probability of failure. We're going to do 10 trials, so we're putting 10 Smarties in a mini box, and we're interested in the distribution, the outcomes of having 0 to 2 red Smarties. Okay, so not 3 or more, because going from 3, 4, 5, 6, 7, 8, 9, 10 is a lot of probability calculations, but if you go from 0 to 2 and subtract it from 100%, we should get what we want. Okay, so the probability of getting at least 3, so x greater than or equal to 3 red Smarties is equal to the indirect methods. You start from 100% and you subtract, so 100% meaning we'll just say start at 1, and we subtract the probabilities of the outcomes that we don't want. So we don't want having 0 Smarties, we don't want having 1 Smartie, and we don't want having 2 Smarties. So we'll do 1 minus P0 minus P1 minus P2. Okay. So using our binomial theorem, our binomial formula, we have 1 minus 10, so 10 choose 0, times 0.3 to the power of 0 times 0.7 to the power of 10. That's for the first one. Probability of having 1 Smartie is 10 choose 1 times 0.3 to the power of 1 times 0.7 to the power of 9. And 10 choose 2, so for the probability of having 2 Smarties, it's going to be 10 choose 2 times 0.3 to the power of 2 times 0.7 to the power of 8. Okay, and remember, we're using, the reason why we're using binomial is because it's either you either have a red or you don't. Okay, so it's a black and white situation. It's 2 possible outcomes: success or failure. All right, so let's look at calculating all of this out. So if we do that, we get 1 minus 0.0282 minus 0.1211 minus 0.2335. Okay, and that's going to equal 0.6172, or we could say 61.7%. So that's a pretty high number. So there is a 61.7% chance at least 3 red Smarties are in the box. I'm talking about at least 3 red Smarties. Okay, so example 4, a jar contains 12 red balls and 8 green balls. 6 balls are removed without replacement. Explain why the binomial distribution is not a suitable model for this problem. Okay, so the jar contains 12 red balls and 8 green balls. 6 balls are removed without replacement. So why is it not a suitable model? You either pick a red ball or pick a green ball. So if you're focusing on red balls, so you pick a red ball or not pick a red ball. Or you pick a green ball, you're not picking a green ball. But why is this a problem? The problem is you're doing this without replacement. Okay, So the number of balls is going to change every time, which changes your p-value and it changes your q-value, and every time you conduct a trial, which would not make the binomial uh, distribution uh, suitable. Okay, so we're going to say here the probability of success changes, okay, with each trial. And because the balls are removed without replacement. Okay, if the balls are withdrawn one after the other with replacement each time, can we now determine the probability that exactly 4 balls are red? Yes, we can. Okay, so let's look at uh, uh, calculating that probability. So if the balls are drawn one after the other with replacement, so now we're replacing them, it keeps the probability values the same. Okay. So if we're removing 6 balls, let's try to figure out our values. So n is equal to 6. Uh, x is equal to 4, so you're going to find out exactly 4 outcomes are red. And the probability is going to be, well, if we had 12 red balls out of 20, so it's 12 out of 20, which is 0.6, and the probability of failure will then be 0.4. Because 0.6 plus 0.4 have to add up to 1. So our probability is using this formula and choose x times p to the x times q to the n minus x. Then the probability of having x equals 4 red successful outcomes is going to be 6, choose 4, 6 trials, 4 of them want to be red, and then 0.6 is the probability of success, raised to the exponent of 4, and 0.4, which is the probability of failure, raised to the exponent of 2. And that's going to equal 0.311, or 31.1%. Okay, so 31.1% of the time, exactly 4 red balls will be withdrawn. Okay, so most of these examples are just singular outcomes, one outcome. Okay, except for this one here, for example, 4, where we did the Smarties problem, where we did a continuum of outcomes. We want to look at least 3 Smarties. So whenever you have to find multiple outcomes, you're going to have to do some additive or subtractive counting probability calculations here. Okay, but that's our lesson on the binomial distribution. There's some practice problems from the PDF text you can work on, or from the practice handouts you have given. And that ends this lesson.